Welcome back to Feedback Control Systems. This is Module 6.2. We're going to discuss Routh-Hurwitz criterion. The objectives of this module are to provide a basic Routh table and interpret that for you, show through basic example how that works, then show a special case, our first special case, where as we go through the Routh table, we end up with a value of 0 in the first column. So only in the first column, and then the special case 2 is if we have an entire row of zeros. So as we go through this, we'll explain what a Routh table is and then the special cases. And again, Routh table, as we show here, what is it and what are we going to use it for? Okay, so we're going to start here. The method that indicates the number, not location, but just the number of right half plane or left half plane and j omega poles without the need to solve for the closed loop poles is basically what the Routh table is going to provide. So again, it will provide the number of pole locations either in the left or right half plane, but not their actual location. Okay, so just enough information to say, is a system going to be stable or not? This method will be useful when we get to design, as it can help indicate a range of parameters for stability. So for example, if you remember in some of the previous module, I might have a gain k and a common sort of denominator, and as I change that gain k, right, maybe the poles kind of come together, and then they go off axis, and then they maybe migrate over to the right half plane. So we might be able to identify a range of k to keep our system stable. Okay, so given a closed loop transfer function, and we've been calling this T of S in previous slides, so I'll just write that down just for sort of notation. A closed loop transfer characteristic, I have an input R, an output of C. I have some numerator N, but what I'm really concerned with for stability is looking at the denominator. So here I'm showing a fourth order denominator. And so what I'm going to do is create what I'm going to call this Routh table. So the approach for creating that is I first look at my highest order term, in this case S4, the coefficient in front of it. Okay, so here's my S4. I'm going to start with the coefficient in front, which is A4, and then I'm going to skip every other one. So instead of A3, which is my S3 term, I'm going to write A2. Then I'm going to skip the next one and go to A0. Okay, so the first row of the Routh table, I start with the highest order value of S, take that coefficient, and then skip every other one as shown here. The next row would be S3 term, and so I'll start with my A3 term right here. I will skip and then go to my A1 term. I will skip, and then I've hit the end of the line. There's no more, so I'm going to complete the table by putting in a 0. So that's the initial population of that Routh table. Okay? So now what I want to do is I want to kind of take the next step. So S3 and S4 here, that's what we saw up here, but now I want to take the next step. So let's focus first on S2. So for S2, you'll see sort of a calculation there. And the calculation, negative times what we'll call the determinant divided by A3. So what I'm going to do for this determinant, notice that determinant is just right there. That's substituted in there. And how we calculate that determinant is that cross multiply. So how we would calculate this, it'd be A4 times A1 minus A2 times A3, have a value there. That'll just be a single value, and then notice there's a negative sign out front of it, so negative of that value divided by A3, which is again this value right here. That'll give us a value that we're going to call B1. Okay, so that's the first entry there that we're going to have for S2. Now the next one here, if I look at this determinant, what is this? Well, that's this column, the first column, and I don't use the middle column, I use the end column right there. So I populate those, calculate the determinant, cross multiply, subtract, cross multiply, put a number there, there's a negative sign out front, divided by A3, which is right there. Similarly here, for this one, notice I'm always dividing by A3 in the row here of S2. Notice also my first column is always the same. Okay? What is changing is my second column. And what you'll see is that second column is what? 1 over, which is this. 1 over, which is this. 1 over, well, there's nothing there, so it's a bunch of zeros. Okay, so we'll go through some methodology here. Some examples to kind of show you how to set that up. Excuse me. That will give us S2. Now we go down another layer, S1. We're going to have a similar format. So next what I do is I take A3 and B1 in this column. Notice that it exists for all in that row. And then I'm going to divide it by B1, shown here. Those are all the same. What is this column right here? Well, that's the previous, or the next one in line, A1, B2. What's this one? Okay. Well, it's this one, which is 0, 0, and then this would look over here. That's also going to be 0, 0. So hopefully you can kind of walk through that and step through, but that is the methodology that we're going to take for completing the Routh table. Now that we have a Routh table, what are we going to do with it? Let's interpret what's going on. What was found as he put this table together is that you can say the system is stable, meaning all of the poles are in the left half plane, if no sign changes occur in the first column. So here's the first column. We're going to look at all of these coefficients, and if they're all positive or they're all negative, for example, there are no sign changes, and we kind of know from the previous module they should, we're looking at positive signs there. So if there are no sign changes in that first column, we can say that the system is stable. Okay? And in this case, because it is a fourth order system, we're going to have 4 poles in the left half plane. We don't know the location, right? We don't know the specific location, but we know the number of poles and the stability. Second bit of interpretation right here is the number of poles that might exist in the right half plane will equal to the number of sign changes in that first column. So if I have a plus, plus, minus, plus, plus, etc., there's a sign change from plus to minus, and then minus to plus. So in that case, there'd be 2 sign changes. There'd be 2 poles in the right half plane. Best to work an example. So first of all, with the example, we have our G of S right here, our forward path. We have a feedback system with unity gain feedback. Now we have our equivalent closed loop transfer characteristic, which again we're going to use as T of S mainly in this course. Again, I strongly advise that you go into our formulation of how do you calculate T of S based on G of S, and see if you can come up with that form of T of S, okay, for the equivalent closed loop system. So from a previous module, what we saw was that if all the coefficients of the denominator are positive and not missing, so again we have S3, S2, S1, S0, they're all positive and none are missing, then stability requires that we solve for the poles. So how we're going to do this? We're going to look at the Routh table. So how do we do this? We take our highest order term, S3, write it there. So the coefficient in front of S3 is a 1, which is here. We skip 1, we go to the second one, which is 31. We skip 1, oh, nothing else, it's 0. So that's S3. The second row we populate. Now we'll go back. We have here S2, which has a coefficient of 10, and then we'll go to the next one, skip, and we have 1030. Then we're done, we have 0. So what I've circled here in red are the initial table, okay? The initial 2 rows. Now notice I've then crossed out the 10 and the 1030, and I've reduced it. So I went from 10 down to 1. So 10 divided by 10 is 1. Well, if I divide this by 10, I can divide this by 10 and get 103. Well, if I divide 0 by 10, I'm still going to get 0. So I can do that reduction just to keep the number small. If I recognize a common multiple, I can factor that out. Again, that would just keep the equation smaller. So you can do that, or you can just stick with the 10 and the 1030 as shown there if you choose. Okay. So that's the setup, and now I want to calculate S1. How do I calculate S1? I do the determinant, so let's clear the ink. Now how did I do the determinant? Well, notice I have this column will always be what I have right there. Relative to these 2, and then these will go right there. That will also be over the 1, which is this one right there. Okay, so then I can do that multiplication, and as I do that, what I will have is a value that comes out to negative 72. Okay, so how do I do that? I cross multiply. 1 times 103 is 103, and then I have 1 times 31, and then I go 103 minus 31, I'm going to get 72, but there's the negative sign outside, so I'm going to get negative 72 over a value of 1, and I'm going to get a total of negative 72. Okay, so for this one right here, I believe there is an error. I think this should be a 1. It's not going to matter because notice it gets multiplied by a 0, so there's really relatively no impact. So I have 1 times 0 and then times 0. So 0 minus 0 is going to be 0 anyway in that column. Okay. So notice again for this, that should be the same as this term here. These should all be the same in that column. This column here really exists from here, and then this, there's nothing there, so I just put zeros. So notice I have my S1 column as shown there, and then I could take those values and create an S0 row that I have here. Okay, and let's clear the ink so we can actually show that just to get some practice. So for the S0 column, notice that is made up of 1, negative 72, as I show here. That's also 1, negative 72, 1, negative 72. The denominator also is that negative 72. It's there in all cases. Now, this column right here is based on the previous 1 over. This is based on the previous 1 over, which is this 0 and this 0. And then these 2 zeros, because nothing exists over here, I can just write in zeros. So again, I think through some practice, you'll start to get this methodology. And the key now, when we are done with this completed Routh table, we can actually look ahead. Notice we look in the first column as shown here, and we're looking for sign changes. So we've identified 2 sign changes going from S2 to S1. It went from 1 to negative 72. That's our first sign change. Then the negative 72 went to 103. That's the second sign change. So they have 2 sign changes. So what you'll see down below with the 2 sign changes in the first column means I have 2 right half plane zeros. Don't know where they are. I just know I have 2, so that means the system is going to be unstable. Okay? And again, from G of S, I look at that. I have a negative 2, a negative 3, a negative 5. They all look stable, but when we have the closed loop system with the feedback, that system turns out to be unstable. Now, what I did is I actually calculated the roots using a program. So I took this polynomial right there, the closed loop polynomial, and actually ran it through some software, set that equal to 0, calculated S, and you'll see those values down below. I have 1 pole, negative 13.4 in the left half plane. Then I have 2 complex conjugate poles in the right half plane, 1.71 plus or minus J 8.6. So the Routh table did predict that case. Now I want to talk about a special case. The first case is going through the Routh table, and what if I end up with a 0 in the first column? Here is our closed loop transfer function, T of S. What I did is I went ahead and calculated this ahead of time. This is a 5th order system, so the actual poles are right here. Okay, and what you'll see is this one in particular, the real part is positive, meaning I have 2 right half plane zeros. The other 3 are negative, so they're in the left half plane. So I already know going into this, it's unstable. But let's say I didn't have access to a computer, and I had to do this sort of by hand quickly. I can generate my Routh table. So the first 2, S5, I take my coefficient of S5, which is 1. Skip 1, I get now 3. I skip 1, and I get 5, as shown there. Then for S4, I start with that, which is 2. I skip 1, I get 6. I skip 1, I get 3. So that's basically the formulation of our first column. Then what I do is for S3, what do I need to do? I essentially need to cross multiply 1 times 6, which is 6, minus 3 times 2, which is 6. That's going to give me 0. That's going to give me a 0. And we'll just kind of step through that. So now I have a 0 in the first column. Now I can certainly do the next term right here. It came out to be 7/2, and then this term came out to be 0. So what do I do now if I have a 0 in that first column? What I'm going to do is I'm going to replace it with a very small number that I'm going to call epsilon. And I'm going to continue, just with a variable called epsilon. Then I can do my cross multiplication for that, and I have 6e let's clear the ink so we can see this a little bit more clearly. So for this case now, for this case right here, I cross multiply. 2 times 7/2 is 7, and then minus 6e, but then there's a negative sign out front, so they'll get flipped, and then it's over e. So I will continue down that Routh table using my variable epsilon here as again a variable, and then I'll continue as I go forth down to the end. In this case, my S0. Okay, so now what do I want to do? I have this epsilon here. I can't tell if my system is going to be stable or not. So what I'm going to do is I rewrote my first column because that's going to determine stability, number of sign changes. So I'm going to say, okay, let's assume epsilon is positive. Well, 1 and 2 are both positive, so they're both going to be positive no matter what epsilon is. So here's my first case for epsilon. Well, if epsilon is positive, that's going to be positive, or if epsilon's negative, it'll be negative here. Then, again, substituting in here, if epsilon is positive, that will turn out to be a negative term, or in this case, if epsilon's negative, it will turn out to be positive. So essentially, I can stop right there. For either case, I've just seen a sign change. I know right off the bat the system's unstable. But I want to see maybe how many right half plane poles, so I can continue down, and then we'll see the remaining characteristics here. So in either case, if epsilon is positive or negative, there's going to be 2 sign changes. So I have those 2 right half plane zeros, which we've already identified right here, and the system is going to be unstable. An alternative way to do this, which does not require this epsilon method, because as you look through this, especially in the row S1, epsilon gets pretty complicated. So there's an alternative method, which is I'm not going to get into the derivation or why this works or how this works, but it works, and I will show it to you as the following. So if we take this characteristic polynomial right here, and if we rewrite it in reverse order, okay, so here I start with 3, then I go to 5, then I go to 6, etc. So I'm basically going this way and writing my coefficients this way, okay? And then I create my Routh table that way. Notice what happens. I don't end up with a 0 in my first column, and I also get 2 sign changes, one from here to here and one from here to here. I also get the same result. Again, they don't tell you location, only that there's 2 right half plane zeros. So this is an alternative, the one I would prefer, but this is a more of a modern sort of realization. The classical one, as invented by Routh, was this epsilon method as shown up here. So either method will tell you, again, if you don't have a computer handy, but you have this characteristic and you just want to see is it stable or not, this is a very quick and easy way to determine that. Our last case here, special case 2, what if we have an entire row that has zeros? So in this case, we have our 5th order polynomial as shown here. We can create our first 2 rows. So S5, again, we start here, has a 1, we skip, has a 6, and then has an 8, so we're skipping. And then everything here, we're going to have a 7, 42, and 56 from the remaining terms that we have here. Now notice all of those are factorable by 7, so I just to keep the numbers easy, made that be a 1, a 6, and an 8. If I look at row S5 and S4, now they're identical. They both have a 1, 6, and 8. What that's going to mean is now my next row, S3, I have all zeros. As you can see with the squared here, they're all going to be zeros. Okay, so I'm going to kind of stop there. And if I have a row of all zeros, here's an approach I can take. I take the polynomial here. I take that polynomial, and if I look at the polynomial, so the row, the previous row, so this is my S3, the row that has 0. I look up one row and I create the numbers. So in this case, a 1, a 6, and an 8, and I write the polynomial as shown there. Okay? But if I know, since I'm in row S4, that's going to be S4 plus 6S squared plus 8. So I have that polynomial. Now if I take a derivative of that, differentiate that with respect to S, I get this polynomial as shown there. So what I'm going to end up doing now is take these terms, going back to my S3, which previously had zeros, and I'm going to replace. So that 4, that 12, and then that 0. So let's clear off a little bit of ink here. It's getting a little messy. So now that's what I have. Again, this 4, 12, and 0 from this polynomial. And then what I do is I factored out a 4 from each of them, and I'm left with a 1, a 3, and a 0. So now I can continue and progress down my table and go forth as shown there. Okay, and so that's what I'm showing there. Now, when I looked at this, I initially looked at the actual poles of the closed-loop system of a -7, plus or minus J2, and plus or minus J1.414. Okay, so none technically in the right half plane. And so notice here as well, I don't have any sign changes there. So that sort of melds and agrees with each other. So in terms of this differential here, I have a comment right here. So an entire row of zeros will appear when there's an even or an odd polynomial that is a factor of the original polynomial. So here's the original polynomial, and in this case, we have a factor here, p of s, that's an even polynomial factor of t of s. So that is a case that we can look out for. And there's 3 general cases that will make this occur for even polynomials. You'll see them here. A, which is you're going to have real and symmetrical poles about the origin. So you'll see A here. They'll be real and symmetrical about the origin. B, they'll be imaginary about the origin. Or in terms of C, you'll see this. There's essentially 4 of these as shown here with that sort of symmetry here. So in this case, what did we have? We have these 2 here and then these 2 here. So sort of the B case that we had there. So don't worry about as much of the math or the theory, I would say, but more of the practical application of what this is showing you. So again, in summary for this module, the Routh table is showing you a methodology without the access of a computer or numerical techniques to quickly determine if the system is going to be stable or not, just by creating this Routh table, looking at the sign changes in the first column. That will conclude this module. If you have any questions on this material, please don't hesitate to reach out. Thank you.